How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at some practice problems for some properties of liquids and phase changes. All right, number one, which statement or statements about viscosity are true? As temperature decreases, viscosity increases. That is a true statement. Viscosity is resistance to flow. So as the temperature goes down, things start moving slower. You know, think about syrup. You heat it up, it gets nice and runny. You keep it in the fridge, it's barely coming out, right? Viscosity goes up as temperature goes down. All right, what about two? Viscosity increases as molecular weight increases. That is also true because typically everything else being kept constant, as the molecular weight goes up, the attractive forces strength goes up, which means viscosity is going to increase as well. Those molecules want to hang out with each other more. It's going to be hard to flow through them or past them and break them apart. Or what about three? As intermolecular forces increases, so does viscosity. Yeah, I feel like I just said that. All right, number two. What factors affect the shape of a liquid's meniscus? So remember, if you filled up a test tube or a graduated cylinder, you might see water makes a meniscus like this. If you had the pleasure of dealing with mercury or something, you might see that, hey, the shape of the meniscus is different. And what's determining, what shape it takes on? Well, we have these particles that are attracted to each other, cohesion, but we also have the particles being attracted to the glass, which is adhesion. And the balance of those determines the shape of the meniscus. So does it have to do with the amount of hydrogen bonding in a liquid? Not directly. So that's not the best answer. B, the relative magnitudes of cohesive forces in the liquid and adhesive forces between the liquid and its container. That's looking pretty good. C, the viscosity of the liquid. No. The type of material the container is made of. Yes, but also B does a better job at addressing that. Right? The material will determine the adhesive forces. But so B kind of is still better than D. And then E, the volume of the liquid has nothing to do with the shape of the meniscus. All right, 3, the heat of sublimation can be approximated by adding together the heat of blank and the heat of blank. So sublimation is going from a solid straight to a gas, right? We could go, hey, solid to liquid, liquid to gas, and energetically, it's the same thing. So if we talk about from solid to liquid, that's the heat of fusion, and liquid to gas is the heat of vaporization. So the estimation of, hey, how much is this heat of sublimation can be added by adding those two together, right? The heat of fusion and the heat of vaporization. Right, Hess's law says that if you add the steps together, should be the overall change. That's pretty much what we're doing there. As illustrated in the heating curve, the phase changes B to C and D to E are not associated with the temperature increase. So if you look from B to C, the temperature stays the same, and then from D to E, same deal. Temperature doesn't change. This is due to the heat energy being used to do what? All right, rearrange the atoms within the molecules. That's not what's happening at all. Break intermolecular bonds. Ooh, careful, intramolecular. So it's saying within the molecule, breaking those bonds? No. Increase the density of the sample? No, usually, in fact, it does the opposite. Increase the velocity of the molecules? You might think that, but the velocity is a kinetic energy, right? And if that changes, then so does kinetic energy, which is measured by temperature. So no. So it's got to be E. Increases distances between the molecules. Absolutely. That's the big difference between the phases. All right, 5. Based on the following information, which compound has the strongest intermolecular forces? So as the intermolecular forces increase, intermolecular attractive forces increase, then you're going to need more energy to do that vaporization. You want to turn a liquid into a gas, it's going to take some energy. The more attracted those liquid particles are to each other, the harder it is going to be to separate them. So which one has the strongest intermolecular forces? It's going to be the one with the greatest delta H vaporization. Number 6, based on what you know about London dispersion forces, which of the following substances would you expect to have the largest heat of vaporization? So largest heat of vaporization means we have the strongest intermolecular attractive forces. So let's take a look. Oh, wait a minute. Hey, these are all nonpolar, which tells me that they have London dispersion forces. And I know if I wanted to increase the strength of London dispersion forces, I need to increase the mass. The bigger the molecule, the stronger those dispersion forces are going to be. So I'm looking for the heaviest one here, and I think it's choice D. There you go. All right, number 7, which of the following would you expect to be the most volatile based on their attractive forces? So volatile means it likes to go from liquid to the gas. So most volatile means it's going to do that the most, which means we want the weakest attractive forces. So if I take a look, oh snap. All of these things again are going to be nonpolar, which means that they have London dispersion forces. So if I'm talking about the most volatile, I want the weakest attractive forces. So if I want to decrease the strength, I need to decrease the mass. So it's really asking me which one is the lightest. Smallest one out of the bunch, it's going to be choice C, CH4. All right, number 8, this is a bunch of math, all right? It says calculate the enthalpy change in kilojoules associated with the conversion of 50 grams of ice at -4 Celsius to water vapor at 106 Celsius. And then it gives us all the specific heats and the heat of fusion and heat of vaporization. So it's basically saying, hey, we're starting at -4 degrees and we want to get all the way up to 106 degrees. And if you know water, you hopefully know that the melting point is at 0 degrees Celsius and the boiling point is 100 degrees Celsius. So we're going to have to break this up into a bunch of different math problems. We're going to have to go, hey, for heating the solid up to the melting point, how much energy is that going to take? And that's going to be the whole Q equals MC delta T. To melt all that water, that's going to be the Q equals MHF. Right? And then once it's all melted from 0 Celsius to 100 degrees Celsius, we're going to have to, again, use that Q equals MC delta T. Then to vaporize it all, I'm going to have to use the Q, that's a Q equals MHV for vaporization. And then once it's all in the gas phase, we're going to have to use the MC delta T again for steam. So let's talk about the solid, one step at a time. Solid, we got Q equals MC delta T. The mass of the water, well, it says it's 50 grams, so 50.0 grams times my specific heat of ice. Let's see, ice is 2.09 joules over gram degree Kelvin, or just Kelvin. And the delta T, well, if I'm going from -4 to 0, my change in temperature is 4 degrees Celsius. So when I do that math, I end up with 418 joules. All right, so now when I melt it for solid to liquid, I'm gonna have to use Q equals MHF. My heat of fusion is 6.01 kilojoules per mole. So I'm gonna have to times this by moles. They told me 50 grams of ice, so I'm gonna have to do, hey, 50.0 grams divided by the molecular mass of water, which is 18.02 grams per mole. When I do that math, I end up with 16.7 kilojoules. Now this is going to be an issue that I'm going to address at the end. I can't add joules to kilojoules directly. I have to convert all my joules to kilojoules. So why don't I do that? 418 joules is going to be 0.418 kilojoules. All right, so that's just to heat up the solid. 16.7 is to melt all this solid. Now that I'm at a liquid, I'm going to have to do my MC delta T. My MC delta T. My mass, again, is 50.0 grams. My specific heat of liquid water is at 4.18 joules per gram Kelvin times the change in temperature. Well, I'm going from the freezing point of 0 degrees to the boiling point of 100 degrees, so my change in temperature is 100 degrees Celsius. And when I do that, what do I get? I get 20,900 joules, which, all right, I'm going to have to make some room, which when I convert it to kilojoules, I get 20.9 kilojoules. All right, so that's to heat up all the liquid. Now from liquid to gas, I go, all right, well, I have my heat of vaporization is 40.67 kilojoules per mole times the moles. Well, again, I'm going to have to use the 50 grams divided by the GFM of water, 18.02 grams per mole. So I get my moles. And when I multiply that together, I get 113 kilojoules. All right, I'm not done though, because now I got to heat up some of this gas. Now the gas has a, I'm going to use the MC delta T again. My M is my 50 grams. My C for steam, they tell me is 1.84 joules per gram Kelvin times the change in temperature, which it's saying I'm going to go up to 106 Celsius. So from 100 to 106 is 6.0 degrees Celsius. Now you may be wondering, hey, that's at Kelvin, this says Celsius. When we're talking about changes in temperature, it's the same thing. If I go up 1 Celsius, I went up 1 Kelvin. So it's fine. So when I do that math, I get 552 joules. 552 joules, but I need it in kilojoules, so it's really 0.552 kilojoules. So now I got to add all these numbers together. I add the 0.418 kilojoules, the 16.7 kilojoules, the 20.9 kilojoules, the 113 kilojoules, and the 0.552 kilojoules. And when I do that, I end up with 152 kilojoules of energy. That's how much it's going to take to do that. And yeah, that's it. I hope you found it helpful. See you in class. Okay, bye.